Alright, so this is question 2 from the 2017 NZQA exam question. And we're told that Sylvia and Sam's spaceship spins clockwise on its axis as it's moving through space. The astronauts can change the angular velocity of the spaceship by firing 2 small rockets that are mounted tangentially as shown. The rockets produce an anticlockwise torque. The rotational inertia of the spaceship is 5.8 times 10 to the 4 kilogram meter squared. Alright. The first part of the question asks us to calculate the size of the torque required, so that's tau, required from each rocket to cause an angular acceleration alpha of 2 times 10 to the minus 2 radians per second. And we're given I here. So this, we're trying to find the torque. We know I and alpha, so we're going to use the equation tau equals I alpha. Which is going to be equal to 5.8 times 10 to the 4 times 2 times 10 to the minus 2, which is equal to, well, 2 times 5.8 is 11.6, and then times 100, so we get 1160 Newton meters. Okay, but that's the total torque, and we want the torque required from each rocket, and there are 2 rockets. So we can say, as there are 2 rockets, each one must provide a torque of 1160 over 2, which is 580. All right, part B, oops, let me just get rid of this. Part B says that a spaceship is rotating clockwise at 0.580 radians per second when the rockets are fired. Calculate the angular speed of the spaceship after 1 rotation. So we can see here that the spaceship is already rotating clockwise when the rockets are fired, but the rockets are going to cause it to accelerate anti-clockwise. So it's going to slow the spaceship's rotation down. Okay. So we have omega I equals 0.580 radians per second. And the angular acceleration alpha is equal to, it's going to be in the opposite direction, so it's going to be negative 2 times 10 to the minus 2 radians per second squared. And we also know theta here, because we're told that it's after 1 rotation, so theta is going to be 2 pi radians, and omega f, oops, that doesn't really look like an omega. Omega f is what we're trying to find out. So here we have a situation where we have a uniform angular acceleration, and we have 3 known quantities, and we need to find the 4th. We're going to use the kinematic equation. Omega f squared is equal to omega I squared plus 2 alpha theta. So we therefore have omega f is going to be equal to the square root of omega I squared, which is 0.580 squared, plus 2 times negative 2 times 10 to the negative 2 times 2 pi, all square root. So let's do that. That's 0.580 squared plus 2 times 2 times 10 to the power of negative 2 all negative. Oops. Let's do that again. 2 times 2 negative to the power of times 10 to the power of 2 negative times 2 times pi, and then we want to square root all of that, and we get 0.292. 0.292 radians per second. So basically the speed is reduced from 0.580 radians per second to 0.292 radians per second as a result of the rockets having been fired. Part C, assume that the torque produced by the rockets is constant. Explain what happens to the size of the angular acceleration as the rockets gradually emit burnt fuel. Well, as they emit fuel, their mass will decrease. This decrease in mass near the rim of the satellite will cause a decrease in the rotational inertia as alpha is equal to tau over I. If the torque is constant, and I decreases, the angular velocity, or angular acceleration, sorry, will increase. Okay, have we fully answered that question? What happens to the size of the angular acceleration as the rockets gradually emit burnt fuel? Yes. Okay. Sometime later, the spaceship is rotating freely at 0.450 radians per second. That's an omega, with the rockets turned off, as shown in diagram 1. The spaceship's photovoltaic cells are then extended out from the spaceship, causing the rotational inertia to increase by 2.74 times 10 to the 3 kilogram meters squared. Explain why the period of rotation changes as the photovoltaic cells are extended. So we can say there are no external torques acting on the satellite. So its angular momentum will be conserved. When the cells are extended, the rotational inertia increases as L equals I omega. Well, we'll say if I increases, omega must decrease to keep L constant. And then if omega decreases, the period of rotation must increase. Because it's spinning more slowly, it's going to take longer to get around. Okay, so this is a typical momentum conservation question where the rotational inertia changes, therefore leading to a change in the angular velocity. Calculate the period of rotation when the photovoltaic cells are fully extended. Okay, so here we need to figure out, so we know omega I, and we know that I initially, we were given that somewhere, we were given that much earlier here. It has 5.8 times 10 to the 4. I initial equals 5.8 times 10 to the 4 kgm squared. And in this situation, I final is equal to 5.8 times 10 to the 4 plus 2.74 times 10 to the 3. And omega f we don't know. Okay, so let's use that information to solve this problem. So we can say Li equals Lf. So I initial omega initial is equal to I final omega final. So then we have 5.8 times 10 to the 4 times the initial omega, which was 0.450, is equal to 5.8 times 10 to the 4 plus 2.74 times 10 to the 3 times omega f. So therefore omega f is equal to 5.8 times 10 to the 4 times 0.450 over 5.8 times 10 to the 4 plus 2.74 times 10 to the 3, which gives us and then what did we have? We had 5.8 times 10 to the 4 plus 2.74 times 10 to the 3 and that gives us 60,740, which seems outrageously large. And that's because I haven't hit equals yet. 0.429. Radians per second. So the final speed is slightly lower than the initial speed. It's only slightly lower because this is just times 10 to the power of 3. So it's only really increased by less than 10%, the rotational inertia, but more like 5%. And so the angular velocity only has to decrease a little bit. Okay, and that's the end of that question.